Hi, welcome to another video. Today I'm going to discuss this little device here. It's a microchip boost converter, MCP1650S. So this is the device, microchip 750kHz boost controller. Here's a look at the PCB I just showed you, and if I zoom into this circuit, so I labelled the FET drain, gate and source. When I connected it to the boost controller, renamed this to X, which is the external FET drive from this boost converter. Drain is still drain, and the source I should have called ground, and because I didn't, I've got no rack line to tell me it's not connected. So that was a mistake, and I only found it when I thought I'd better see if all of this works, and it didn't. So if I get rid of the top layer and bottom layer, you see the inner layer, get rid of that, there's one inner layer, and there's the other inner layer. So here's the simple schematic how to use this boost controller. So it's currently running on 2.6 volts in. You can connect the V in directly to the CS, then that doesn't sense any current. However, if you don't connect the CS to V in, put a low value resistor in there, something like 0.1, 0.01 ohms, 0.05. When this CS detects a voltage drop, it says here, of 0.12 below the V in, it will stop switching the FET. That's to protect this FET. So depending on what value resistor you have determines how much protection you have on your FET. Now this little SOT23 is actually a 4 amp continuous current, and the gate threshold is something like 0.6 of a volt. So this is a circuit. I've got a 3.3 microhenry Coilcraft Schottky diode, which is just a fast diode. You saw 6 LEDs chained in series. You get approximately 2 volts drop across each, 22 ohm connected to ground. So I'll show you on the scope. Without this resistor connected, with this setup, with a 9k resistor here and a 1k resistor here, we get approximately 1.22 volts up here. Because I had 1 and 2k resistors, that's why I've got 1k and 9k here. However, the feedback only requires 50 nanoamps. This is currently 1.2 milliamps. So it's something like 24,000 times more current here than I need. So I could actually change this to 90k and 10k. Right, so here's the board again. 1, 2, 3, 4, 5, 6 LEDs, 22 ohm resistor. At the moment I'm powering the LEDs directly from the power supply. Here's my power supply lead to the LEDs, ground over here, 12.2 volts, 20 milliamps, and the scope says 12 volts. I'll disconnect this power supply and power up this boost circuit. You can watch as I turn up this supply. There we go, it's cut in here. 2.5, 2.6 volts, 110 milliamps. And like the schematic says, 12.1 volts out. But this is the cost of a boost converter. That's over 5 times the current at 2.6 volts to get that 12.1 volts at 20 milliamps. So we've got 130, 140 milliamps with approximately a 20 milliamp load. But if you've only got 2.6 volts and you need more, something like 12, this is a great circuit. So we are at the moment drawing approximately 140 milliamps through this inductor. The saturation point on this inductor is 1.4 amps, at which point it gives you no more energy, it just starts getting hot. That's one of the important factors. You've got to look at what's the saturation current, is it above what you're doing, and is the resonant frequency above your switching frequency. Well, so this is me probing the drain. I'll capture this. Turning on 4 times there, pause, on 4 times, pause, 751.9 kilohertz, voltage peak to peak 14.7, pulse width 250 nanoseconds. Right, I've now soldered on that extra 100 ohm across the LEDs, so we've got 20 milliamps through the LEDs plus this 100 ohm. Now I did have 120 ohm, it's actually better. Sometimes this doesn't want to start at 2.6 volts, you need to turn it up to 2.7. So we are on the limits of what we can get out of this 3.3 microhenry coil. So 100 ohm, let's look at what the gate is doing. This is now the drain. And you will see we've got no missing pulses. The frequency's gone up to its max, 753 kilohertz. Still 14 volts, same pulse width roughly. And you see no missing pulses. So this is continuous operation. So with the extra 100 ohm load, the voltage come down from 12.1 to 11.5. I had to turn this up from 2.6 to 2.7 to get it to cut in, but look at the current, 740 milliamps. So from 2.7 volts to 11.5, but at the cost of the current, 740 milliamps. So you don't get something for nothing. This is a 6.8 microhenry, 150 milliamps, 18.2 volts. Load it up with a 100 ohm resistor, drops down to 10. Intermittently it's dropping pulses. That's for the 6.8 microhenry. This is without the resistor, 140 milliamps. With the resistor, 630. So we still need more current to get 100 milliamps at 18 volts. So that 6.8 microhenry is still too big. So I put this 2.2 microhenry inductor back in. I've got the supply to the LEDs, just so you can see they're drawing approximately 20 milliamps, just below 20 and then 20 at 18.5 volts on this display, and my scope is showing 18.3 volts. So the figures I give for this circuit are approximate based on the assumption these LEDs are drawing 20 milliamps. Let me reconnect this power supply to the input. Right, that's the circuit with the lights off so you can see all 9 LEDs are on. I've got a scope probe measuring the voltage here and the other scope probe over here measuring the power supply input voltage. Remember, 2.2 microhenry coil. Let me show you the power supply. So that's the power supply showing 2.8 volts, 700 milliamps at 2.8 volts, but actually that voltage is 2.6. So we've got the minimum going in 2.6 and we've got 16.9 out. This current inductor is the most voltage and current I could get out of all these inductors, from 1 microhenry all the way up to 10 and 15 and 100. So I'm back down to 2.2 microhenry. It could just be the saturation current on all the other inductors. I am only able to measure the average. I cannot see the peak current going through the inductor. So this is the input voltage, 2.6, and we've got 16.9 out. That's the most I could get. So now if I turn the input voltage up to 3.3, which is my microcontroller voltage, there we go, 3.3 here, we've got 18.1 out. I could not get that with a 15 microhenry inductor, this one here, with a saturation current of over 1 amp. So remember, 3.3 in, but the power supply says 3.5, and we've got at the moment 690 milliamps. Earlier it was 730 milliamps. So it looks like the efficiency has come up. but my figures will put you in the ballpark of the efficiency of this circuit. If we turn up the voltage past 3.8, the duty cycle will switch from 80% to 56%, so this current will go down. Are you watching? Turn it back a bit. So we've got 720 milliamps there. Watch for when it goes over 3.8 here. I had to wait for the fan to come off on this. Right, watch this current drop. I think that's just dropped now. So we're from 700 odd down to 520. The duty cycle has just swapped from 80% to 56. Now we can turn the voltage up to a maximum of 5.5. Right, this is 5.5, my scope says 5.2, and we've got 18.3 out. I don't want to turn it up any further in case I'm not measuring the voltage properly. That chip will get destroyed over 5.5 volts. But you can see, so with 5 volts in, which is there, 5 volts in, 460 milliamps. And we've still got the 18.3 volts. And we've still got 9 LEDs, 20 milliamps. I've changed the feedback network to 14K from 9K, and I've changed the load. I could not get 200 milliamps out of this circuit. I've got 200 ohm resistors shorting this output to ground. I shortened the current sense wire, put it straight to the voltage in. As I say, this 2.2 microhenry gave me the most power out. As you increase the inductance, the current will go down, or you can't necessarily consume the amount of current you want up at a certain voltage. Here's a look at the output from that microchip chip. This is the gate pin. So you can see there's a bit of a mess here. If I capture it, you can see we've got a pause there. Various pauses. So 750 kilohertz as per the spec, but intermittent pauses, which means this is running in non-continuous mode. We've got 752.5 kilohertz. Right, so we've got 3.3 volts in, duty cycle, roughly 80%. If I turn the voltage up, once it goes over 3.8, you see the duty cycle cut down to 56%. Watch the voltage come up. There we go. Doesn't seem to be 3.8, so 3.4. 3.6, and you see it's dropped down to 55.8%. And now with the higher voltage, the smaller duty cycle, notice there's no missing pulses, so this is continuous mode at 56% duty cycle. Looking at the frequency, it's gone up 778 kilohertz. So that's the gate, and that's the duty cycle. Turn the voltage back down. 3 volts in. 80% duty cycle, non-continuous mode. But hopefully we don't get too many artifacts with this camera pointing at the screen. It's the same circuit as before. Now I've got 2.2 microhenry coil, same FET. I just showed you the gate here. I changed my feedback to 14k and 1k, so this 14k will drop 16.89, so we have 1.2 here. This is actually passing approximately 1.2 milliamps, which is thousands of times more than this feedback actually needs. So 9 LEDs, 20 milliamps approximately. So with no additional load, the 20 milliamps, 18.2 volts, 2.6 volts input current 190 milliamps, falls to 150 milliamps at 3.3 volts in. So we've got 0.494 watts in at 2.6 volts. The output, with no additional load, 0.364 watts out, 73.6% efficiency. Turn the power supply up to 3.3 volts. The current falls to 150 milliamps, 0.495 watts in, 3.3 volts, 73.5% efficiency. So at light loads, that's the approximate efficiency. However, increase the load, it becomes more efficient. So with the extra load, 18.1 volts out, 3.3 volts in, current 730 milliamps, 2.4 watts in, that's 83.3% efficiency. Turn the voltage up to 5 volts on the power supply, current falls to 470 milliamps, with 5 volts in, 2.35 watts in, 85% efficient. The total load current 110 milliamps at 18.1 volts approx. So we've got 2 watts output and between 2.3 and 2.4 watts in. I expected that sort of efficiency. So that just leaves one more test. Here's a lithium ion battery, 3.7 volts. So ground over here. Still got the same load, 100 ohm, and the LEDs. So roughly 3.7 in and approximately 18 volts out. Hopefully you've got a better understanding of boost converters, and specifically the Microchip MCP1650. And increasing the value of an inductor isn't always the way forward. And you've seen the current on the power supply, the input versus output. If you need to boost the voltage by 5 times and have a decent amount of current, you need a large amount of current in. The current is the price you pay for a boost converter. Hopefully you enjoyed this video, hopefully you learned a thing or two. Thanks for watching.